Hello, chemistry students. We are going to begin our very last and final topic. And I promise, because we worked so hard in Chapter 10, that this is going to be, I think for most of you, this is going to be pretty simple. And the truth is, we've done a little bit of this already. So this concept of stoichiometry really falls along the lines with the molar conversions. And this is looking at the balance equation and really making predictions about how much of, if you have this much of one product, how much of another product do you need for that to react. So stoichiometry is used to make predictions of either the amount of reactions or reactants needed or the amount of product that might be produced in a given reaction. And as I mentioned, it uses the ratio of reactants and products in a balanced equation. So, for example, if I have the equation, remember what we know when we look at a balanced equation. So we know if I look at this equation, so this is a very simple one, obviously, the equation for water. This tells us that, and we could say it's 2 moles of hydrogen, H2, plus 1 mole of oxygen yields 2 moles of water. I could also say 2 molecules of H2 react with 1 molecule of O2 to produce 2 molecules of water. But for the case, when we're talking about stoichiometry, we're really going to say, we're going to use the molar conversion, okay? And again, we did this in an earlier lab. We actually did, we've talked about this before, so this is not new. So this hopefully isn't too confusing for you. So from this balanced equation, these are the 3 conversion factors that I can take from that I can get from that balanced equation. So 2 moles of H2 are used for every 1 mole of oxygen. That's what this right here tells me. That if I have 2 moles of H2, it will react completely with 1 mole of O2. So I know that this is a true statement, so I can use this conversion factor, and I can flip it either way because it's a conversion factor. The next one, 2 moles of H2, so 2 moles of hydrogen gas, which is H2, can produce 2 moles of water. So I'm looking at this one. I just realized I couldn't write on this. Anyway, so 2 moles of H2. So we're comparing this, the H2, as one of the reactants. And in a complete reaction, it can produce 2 moles of water. It can't do that without the oxygen, but I can make a conversion factor between anything in this balanced equation. And then the final, from this balanced equation, the final conversion factor I can get is 1 mole of oxygen will produce 2 moles of water. Of course, that means with sufficient hydrogen gas, which is not referred to in this conversion factor, but it doesn't need to be. So what this means is if we know the mole ratios, we can make predictions about what is needed or what quantities can be produced if we know some of the quantities, okay? So I think one really easy example, so this is how I would explain this, or a super simple example of this. So let's do an example. Let's say that I have 35 moles of oxygen. Okay, so let's say that, here's a good demonstration of using stoichiometry. Let's say that I want to make a s'more. And in order to make a s'more, I need to have the right ratio of ingredients. And before I can know my ratio, even though a s'more is super simple, but I have to come up with a recipe, right, for how to make a s'more the right way. Now, I know there's lots of variations, so we're going to keep it to the simple basic, what a s'more is. I know some people use fudge stripe cookies and all kinds of yummy, different kinds of cookies and whatever. But we're going to make a basic s'more. So I need to come up with that basic recipe of how to make a s'more. And that's really what a chemical reaction is a basic recipe. It'd be fun when you guys are at home and you're going through this. You should totally make a s'more. You'll know what I'm talking about. If you were here, that actually is what we would be doing. We'd be making s'mores. So my heart's a little broken. I don't get to do that with you. So do that at home. My recipe for making a s'more . 2 squares of graham cracker, 1 marshmallow, okay, so this is the best I can do. 2 squares of graham cracker, 1 marshmallow, and I know some people like to double up that marshmallow. You could use a strawberry marshmallow. The original recipe is just a regular marshmallow. They're awesome with strawberry marshmallows. 1 square of chocolate. And if you buy the Hershey bars, it's really like 3 of those little squares. We're just going to call that 1 square to keep things simple. And that makes 1 s'more. So this is our product. These are our reactants, and this is the ratio. So there's a lot of, this is balanced. This is really how much it takes. And I'm going to, so a s'more really is a combination of chocolate, marshmallow, and graham cracker, right? So if we wanted to write the sort of chemical formula for a s'more, it would be, like 2 graham crackers of marshmallow and a square of chocolate. So mass is conserved. So the relationship of moles I can get from this would be, I could say, I'm deciding if I want to write all these out because we did this earlier in the year. I do remember that. So if I look at all of the relationships between any of the reactants and products in this balanced equation, this conversion factor, I can get 1, 2, 3, 4, 5, 6 different conversion factors. I'm literally comparing each of these ingredients or products to every single other ingredient or product, just one at a time. So 2 squares of graham cracker for every 1 marshmallow, 2 squares of graham cracker for every 1 square of chocolate, 2 squares of graham cracker with these other ingredients will produce 1 s'more. That's the ratio. And then I went back to marshmallow and said, okay, I need to compare marshmallows to squares of chocolate, marshmallows to s'mores. And then the very last thing, squares of chocolate to s'mores. So any of these conversion factors can be used in this equation. So who cares, right? So what is the relationship? Well, here's what we can do with this information. What if I'm having a big old party and I have to make 175 s'mores? So, excuse me. So let's say that I have to make 175 s'mores. I'm only in charge of bringing the graham crackers, okay? Someone else is bringing the marshmallows, someone else is bringing the chocolate, but I am responsible for bringing the graham crackers for 175 s'mores. So here's sort of what that equation would look like. All right, so I need 175 s'mores, and I need to know how many graham crackers that's going to take. Well, I know you can do this in your head, but remember that's not the point. The point is to set this up the right way. I'm going to stick to really simple equations with this, but it gets more complicated, okay? So 175 s'mores, which conversion factor would possibly get me from s'mores to graham crackers? So s'mores to graham crackers, s'mores to graham crackers. I'm just looking here and I just need to find one that has graham crackers and s'mores. Oh, look, here we go. Bingo. Remember how we set these up? I'm going to multiply it by a conversion factor. I need to end up with graham crackers, so I actually need graham crackers on top. So I need 2, and again, squares of graham crackers for every 1 s'more. I have 175. I need to make 175 s'mores. Remember that this whole number is like a fraction over 1. And this is 1 s'more. Sorry, writing with my mouse. I know this is the worst. So obviously, I'm just taking 175 times 2 divided by 1, and nobody cares about the 1, right? All right, so I need 350 graham crackers. Now remember, I'm only talking about s'mores and graham crackers, but I need to have, enough of these other ingredients as well. But since I'm not in charge of that, I'm not going to worry about those right now. Okay, but I know if I'm in charge of bringing the graham crackers, I need 350 graham crackers. So how would I set this up if, let's say I'm looking at the equation for water, I have 35 moles of oxygen, how many moles of water could be produced? So I'm going to set it up the same way. It's that recipe. So I have 35 moles of oxygen. I want to go from moles of oxygen to moles of water. What equation or what conversion factor goes from moles of oxygen to moles of water? This one is hydrogen and oxygen, hydrogen and water. Oh, right here, right? Moles of oxygen to moles of water. Remember, I can flip this, and clearly I'm going to have to because I want to end up with water, so water has to go on top. So, 35 times 2, that would be, oopsie, that's a 7, 70. So 70 moles of water. Remember, I have to have enough hydrogen. I can't run out of that, but if I have sufficient quantities, yeah, I can produce 70 moles of water. Let's do one more example. How many moles of oxygen will be needed if I have 7.25 moles of hydrogen? So I'm starting with 7.25 moles of hydrogen. And I want to get to moles of oxygen. So this is moles of, and it's hydrogen H2 because hydrogen is diatomic. I want to end up with moles of oxygen. And again, that is also diatomic. My conversion factor, I need to get rid of hydrogen and end up with oxygen. So yeah, actually this first one right here, but I'm going to have to flip it. If I do the calculation, so 1 mole of O2 over 2 moles of hydrogen, if I do the calculation, 3.625 or 3.63. So this is, remember, this is like my recipe to see how much I could produce there.